The title is very sort of broad of this talk, but I want to quickly start by just motivating a little bit this sort of very broad title, similarly as I did in the abstract. So I want to claim that computation is not that far from logic and in fact from mathematics. So there is a sort of an algebraic tradition, sorry, not algebraic, algorithmic tradition in mathematics and logic. And it goes back at least to Euclid, and everybody knows about the proofs of Euclid, which involve construction and calculation steps. Jumping ahead a couple of 100 years, we know about Leibniz, and we know about how influential Leibniz was on some later logicians, for example, Frege and Hilbert. And he had this idea of calculating these concepts, which was arguably calculation. So I claim that there is this connection here. Of course, then there is the constructivist and intuitionist tradition. I put up here some names to drop some names, Kronecker, Brouwer, Heiting. And I want to actually argue, or I would argue, that the two other sort of approaches to the foundations of mathematics around the turn of the 19th and 20th century are also heavily involving the calculi and proving things. So the idea of proof may be in different senses, but it's also present in the formalist tradition as well as in the logicist tradition. And of course, sort of, again, jumping ahead, so we do consider in logic axiomatic calculi, sequence, resolution calculi. So the idea of computing and logic is, I want to say, it's very old. Now, on the other hand, there are models of computation, and here I put up the first is combinatorial logic, which is one of my favorites, but there are also the lambda calculus, the Markov algorithms, and these are very sort of logical kind of models. On the other hand, there are the Turing machines, the counter machines, and these are actually related to the abacus machines that I will be talking about. There are the ACMs, which is not the Association for Computing Machinery, but the end branching counter machines with zero test, and the abacus machines that I want to talk about. So everybody knows that, at least since Hao Wang, there is a very easy idea about, a very straightforward idea how to describe in a first order language the tape and the steps up, for example, of a Turing machine. Or more recently, and this pertains to more closely to the topic of this talk, propositional linear logic is claimed to emulate, in some sense, the ACMs, so the end branching counter machines. I also put up here a quote from Kripke from a chapter published in 2013, where he argued that the Church Turing thesis is really provable, and the claim is, or the sort of the motto, so to speak, is that the idea is behind this claim is that that computation is a special form of mathematical deduction. So turning now to some logics. So some logics are, of course, decidable, and we know this. Here it's a sort of a short list of propositional logics, like two-valued logic. I think that we can claim that it was shown to be decidable in the sense of the completeness theorem by Emil Post from 1920, or by another completeness theorem by Kalmar from 1935, via the semantic equivalence between proofs and the semantics. Of course, there is the intuitionistic logic, logic proved decidable by Gentzen in 1935. McKinsey used some algebraic techniques to show, for example, S4 decidable. And of course, there is the decidability proof of the implicational fragment of entailment and of relevant implication, and also of the strict implicational version of S4 by Kripke from 1959. And you probably noticed the stars. By these stars, I refer to proofs where actually sequent calculi are used. And this is, again, this is what pertains to the rest of the talk. And so I'm not going to, of course, do an overview of various kind of decidability methods. I'm focusing on sequent calculi. In that context, an interesting comparison is Gentzen versus Curry. And here the interest is in that, in some sense, Curry is more constructive or more algorithmic, if you wish, than Gentzen. Gentzen originally was considering sets of sequence, and he sort of imagined that because these sequences were all reduced sequence, so there were finitely many of them, you can as if move a certain sequence from one set into the other. And after a while, this process has a fixed point, and then you can simply look at the two sets and see whether the desirable or the sequence that we were trying to prove is in the set that we were constructing or filling up, so to speak. Now, this is a completely different idea than what is most often used these days, and that second idea goes back to Curry into 1950. Curry came up with the idea that we could construct a proof search tree instead of this sort of moving sequence around sort of idea of Gentzen. And in this proof search tree idea, there is a problem, of course, that we have to make sure that the tree is finite. And so if we would consider Gentzen's proof in this approach, then the magic number is 3. I put here a smiley face in brackets, so some of you might sense here an attempt at humor. Actually, it's an overkill for the right-hand side of a sequence by Gentzen, but 3 works as 4 would work as well, and 5 and any other finite number that is greater than 3. So Curry's method or Curry's idea was to deal with this problem of finitizing the search space, is that he proved a lemma, which is nowadays either called Curry's lemma, or it's called height-preserving admissibility of the contraction rule. Curry's lemma is much shorter and easier to say. And to achieve this, he required that contractions in every operational step happen, which was a possibility because he was looking at the positive fragments of two-valued logic and intuitionistic logic, so without negation. And so there was no problem with respect to having sinning built into the axiom. I think I promised I promised a quick overview of what I call the Curry-Kripke technique. And this is essentially adds what Kripke added to this idea that goes back to Curry. And by the way, it was also very much popularized. And so many people know this not from Curry, but know from Kleeny's book on the, whatever is this 1952 famous textbook that Kleeny wrote, has titles of something like the Introduction to Mathematical Logic or something like that. So the main steps here are the following. First of all, we have a sequent calculus, let's say for logic X, that is going to be denoted by Lx following, let's say, Gentzen. And we do want to have the cut rule admissible. In general, if there is no cut rule, then it is very difficult to see what the logic is doing. It's most likely not structural in the sense of the Polish school. So the replacement theorem is hard to prove, perhaps. And if the cut is not admissible, then of course it means that there isn't as much control over the proofs as we would like to have, perhaps, if we can just use cut-free proofs. So once we have this sequent calculus, then what we want to do, and this is the novelty that Kripke introduced in his 1959 abstract, is that we can build a sequent calculus in which there are permitted contractions. So the contractions are not required, as in the case of Curry, but they are permitted. And of course, the cut rule should be also admissible, and the amount of contraction in each step is finite. It's not necessarily predetermined in a sense, the amount of contraction, because it depends on the size of the sequence, but there is only a finite amount of contraction that can happen. Then, well, if the cut is again admissible, then one has to prove Curry's lemma, or the appropriate version of Curry's lemma for this sequence calculus. Then one can appeal to Kripke's lemma. And I put here in the first bullet point the sort of the sequence calculus related version of this lemma, sequence of distinct cognate sequence in which contractions of later elements do not yield earlier ones is finite. I have to mention that Kripke, in fact, did know that there is a more general lemma that pertains to natural numbers or number theory. And it's well, it's more general in the sense that it's not specific to sequence calculi. And so here is an attempt to formulate such a lemma. I hope that I didn't mess this up. Given a positive integer n, there are finitely many positive integers m, let's say, such that m does not have a prime factor that is not a prime factor of n, and m is not a multiple of n by its prime factors. So Kripke's lemma, in fact, is very general. However, it was introduced in the context of the sequence calculi, and both the permitted contractions and the use of this lemma in the context of sequence calculi is a novelty. That was a novelty in Kripke's proof of the decidability of the implication of fragment of entailment and relevant implication. And then, of course, we want to appeal to Koenig's lemma, or if you are hardcore constructivist, then you might instead use Brouwer's Venn theorem. And then we constructed a proof search tree, and by the combination of the three lemmas, Curry's lemma, Kripke's lemma, and Koenig's lemma, the finiteness is guaranteed. And so if the proof search tree has a subtree that is a proof, then the sequence is provable. Otherwise, we have a finite tree, and if it doesn't contain a proof, then we know that the sequence is not provable. I put here 2 and 3 into red to remind myself that I should point out that what sort of varies between logics, so one sequence calculus and another sequence calculus can differ with respect to how these permitted contractions are built in, and that impacts also the proof of the Curry's lemma. But Kripke's lemma, as I said, is general, applicable. The Koenig's lemma is so old that well, we don't even know when it was introduced exactly. And so these two and 3 are the specific theorems or claims that need to be proved for each particular logic or sequence calculus. As an example, here is the sequence calculus, that is the implication of fragment of relevance logic. As you can see, I formulated this here with sequences. So there is an exchange rule or permutation rule, and the building in the contraction, since there is only left contraction. So the calculus that builds in a contraction, it builds into the left introduction rule of the implication, and the part in red is intended to indicate that some contraction can happen there. In particular, the number of occurrences of A implies B can be reduced by 2 if it occurs both in gamma and theta. And the other formulas that might occur both in gamma and theta can be also reduced by 1. So that's what the brackets are intended to indicate in this red part of the sequence calculus. And I also, since I don't need space here for the contraction rule, I added here the cut rule just to, not to have too much empty space on the slide. So this is the cut rule, which is admissible both in the LR sub arrow and in the second sequence calculus. So I claim that this type of proof has been extended to some other logics, and I divided the potential extensions into three categories, so to speak. The first one is when there are more connectives or other connectives in the logic. And this started off, so Kripke's proof was 1959. It was communicated to Belknap in 1959. And Belknap and Wallace in 1961 extended that proof to the implication negation fragment of the entailment logic. And if you take a look at this, then you can see that it's a very complicated extension, and that probably pertains to the fact that the entailment doesn't behave very nicely in terms of a sequent calculus because of the fact that it has these restricted versions of permutation and various other restricted axioms. For the purposes of this talk, specifically interesting is Meyer's extension of the Kripke method to the LR logic, which is not the sequent calculus version of R, but it's the so-called lattice R. That is, it is the R without the distributivity axiom in axiomatic formulation. And it's in fact not, so distributivity is not provable in LR. So the conjunction and disjunction are not, do not distribute over each other. And then I think there is a very nice presentation of the extension of Kripke's method to the implication negation fragment of R with two, so both on the left and right hand side of the sequent calculi, multiple formulas can occur, and this is in Dunn's handbook chapter from 1986. Now, another way to extend this method, I claim that we proved the decidability of ticket entailment, implication of ticket entailment. And here the idea is to simulate irredundant proofs in this logic, which essentially the logic that I showed you, except that it adds this little t, and those proofs are simulated in this other calculus, which has this funny label, the LT, little t circled, and the arrow. Yet another way to extend, and again, I do claim that we have proved some logics decidable. So I do claim that we have proved linear logic decidable in 2015. And the problem here is that some of the structural rules in linear logic are modalized, or they are exponential formulas that can be contracted and sent in. And so the idea here is to show that the relevant version of the appropriate calculus is decidable, and therefore there are irredundant proofs, and from that we define what we call heap numbers. These are not Meyer's heap numbers. We define something that we call it heap numbers, and that can be viewed as a bound on the size of the proof that needs to be considered, because it bounds the number of contractions that needs to be considered. And this contradicts to the undecidability results by Lincoln, Mitchell, Shankar, Shadrov, Shankar on one hand, and by Kanovich on the other hand. And I do make here a conjecture that in my view, Dunn in fact knew since 1992 that LL was decidable, and the basis for this conjecture is that he is the person who introduced the sequent calculus for the positive fragment of R, the LR plus calculus. And I think he knew very well that, for example, there is no correct cut elimination proof in the paper by Lincoln, Mitchell, Shadrov, and Shankar. Now, the same sort of idea can be used also to some other fragments, I should say, of linear logic. For example, MEL, the multiplicative exponential linear logic, and NLL, which is, I call this the normal linear logic. It's a little bit more than the normal linear logic. And here it is, so NLL. I tried to use here the original notation by Girard. And so you can see that, well, this is sort of this is like the implication connective. This is like the disjunction connective. This is like what relevance logicians call fusion. And this is the so-called fission. And here are the rules that introduce the exponential connectives and these 4 structural rules that are modalized. The normal linear logic that was that was defined by Kopilov, and that would further restrict that would restrict the this calculus that is here on this slide by also restricting the shape of the sequence that can occur. But so it's a little bit more, as I said, than what the normal calculus would be. But if this is decidable, then normal linear logic is decidable as well. So what could go wrong in particular in an undecidability proof? Well, for example, it could be the case that the cut rule is not admissible, or not even claimed to be admissible, as I believe Kanovich doesn't claim it admissible, in which case it's not clear that the series that are claimed to be encoded in full linear logic are in fact completely encoded in the sense that we can just look at the cut-free proofs in linear logic instead of using this theory. Additionally, in which case we would have potentially consider cut as a rule, and then of course the proof search would not work. So that would be a different claim, not the decidability or undecidability of the logic. I mean, it can be the case that the cut proof is incorrect, and for example, Lincoln, Mitchell, Shadrov, and Shankar do have a cut proof. They do claim that they prove the cut admissible, and in fact, they do use this particular method of proving the cut admissible in defining something called the directed cuts, and that is again essential for the claim of encoding the mole series, which captured the ACM instructions into full linear logic. Now, I put in here a little bit of a self-advertisement. So, of course, in some sense, the fact that the cut proof is incorrect is not a problem, because one could prove the single cut rule admissible. And one way that I think that it is very elegant, of course, it's something that I did, so I'm very biased on this. For example, using triple induction, using a new notion, contraction measure, fixes this problem. So this goes away. And of course, there might be minor mistakes like defining wrongly the initial states or whatever states. So now I would like to focus on the problem that whether the AAL proofs indeed encode computation or they don't. And well, if we have a proof which starts with the axiom Q sub f, so the final state implies this final state, and or if we are in the one-sided calculus, then one of the atoms are thrown onto the other side as a negative one, and we end up with the sequence that is claimed to say that from the initial state, using certain instructions in an ACM, we can get to the final state. So there is this proof. Well, then we definitely have a path, so to speak, in this machine, so to speak. But the question is which direction this path is going. So is it going really from the initial state to the final state or not? And here are 2 points to consider. And I think that the consideration of these 2 points shows that we are not looking at AAL proofs modeling computation in ACM. So if the AAL proofs model computation in ACMs, then there should be proofs that model computation from the starting state, let's say Q sub I, to a dead end state, what I quote here Q stuck, because the machine is stuck there. However, there are no such proofs in AAL. So just absolutely, there are no such proofs, because the proofs in AAL always start with the final state. Now, two, if the AAL proofs would model computation in the ACMs, then there cannot be proofs that model, and here the square quotes is the sort of the philosophical use of the square quotes when what is inside of them is not what it really is. So I said in square quotes computation from an inaccessible state Q extra to a final state Q sub F. But the computation is in square quotes because, well, by definition, if the state is inaccessible, meaning that from the initial state there is no computation that goes through that state, then of course there is no computation from that state to anywhere. However, there are such proofs in AAL, so one can easily construct such proofs. It is a completely different issue that, probably if you try to construct an ACM, then I suppose it's very infrequent that somebody would just throw in for fun extra 10 states, because why not, and connect them to the final state. But the definition of an ACM doesn't exclude that possibility. And in fact, it's easy to construct an ACM that has such a state and show that there is a proof. And we did this, in fact, in our paper. So let's now turn to the, I also promised to talk about the reverse computation in the finite state automata and transducers. So finite state automata. So here is an example. This is a little finite state automaton. There is a set of states. Q, sigma is the alphabet, Q, S is the start state, F is the final set of final states, and delta is the transition function. And here is the picture. This, in fact, can be taken to be a representation of the of this machine. And this is the language that is accepted by this finite state automaton. It's obviously a regular language. I just used a regular expression to define it. So it goes, so I'm sort of assuming that everybody is more or less familiar with these. And so, so this is an example. Now, if we take a look at the transition function, so this is a deterministic machine, then we have these triples. And you can see that, so first of all, the triples are sort of represented in a flat manner, as we usually do with n tuples. So we sort of tacitly assume that we could consider the angle brackets as if they were associative, so to speak. And it so happens that if you now take a look at not delta, but so delta was taking the first two elements of the triples and associating the third one, so that was the function. But we now take the second and third, and we take a look at the first one, then it happens to be accidentally a function. So I constructed this example so that the sort of two-way view of these triples, in fact, is a function both from the first two elements toward the third and from the second and third toward the first. But that's completely accidental, or well, accidental in the sense that I intended to show this, but it doesn't need to be like that. And so here are some potential problems. So first of all, it can be the case that the set of final state is not a singleton. So if I want to reverse the arrows, as in this picture on this page, then that would mean that I have several initial states, and that's not in accordance with the definition of a finite state automaton. And it is also possible that there is more than one incoming arrow with the same label. Again, that doesn't happen here. So I can take here this as an initial state, and no state has more than one arrow with one particular label that comes in. So this is in fact just taking the previous finite state automaton and reversing it in the sense of turning around the arrows, so to speak, and declaring that this is the initial state and this is the final state that was previously the initial state. The problems that I mentioned are inherent, and here is a sort of a quick proof of that. So we can have a language, for example, the AAL star language, and if we are considering deterministic finite state automata, then this is going to be the one that computes that. And using the pigeonhole principle, it's easy to see that there must be a state. In this case, it's QF, which has two arrows. Here is one, here is the other arrow coming in. So the inbound arrows with the same label. And so now if I reverse this, then I have to go out, so to speak, on two arrows with the same label, and that's against the deterministic feature of the finite state automaton, of the deterministic one. Now, just taking the same language as if, but throwing in another letter and then taking their union, we can construct this finite state automaton. And it's easy to see again that I cannot make the two final states the same. So QF sub 1 and QF sub 2 cannot be made the same, because then I would modify the language. So, so this sort of a preamble, so to speak, to the question what should be reversing. So the original suggestion, what I was making tacitly or maybe implicitly, or is that we just reverse the arrows. So we could also think about, I put here one, I'm not sure whether anybody would think about this, but so the finite state automata are thought to be sort of informally described as scanning the string. And so we could then consider scanning the string backward. Let's say if we originally scanned from the left, then we would now scan it from the right. Well, the reversal of a string and the reversal of a language is well-known operations in formal language theory. And we do know that if L is regular, then the reverse L is also regular. However, the two finite state automata do not necessarily need to be related to each other at all. So it's not really the notion that I'm after in this talk, or in the sense of reversal that I want to consider. So if we reverse the arrows that I was suggesting, then we can, of course, say that, oh, the finite state automata, if it's deterministic, then there is a problem. But let's then simply say that we are going to deal with non-deterministic finite state automata with epsilon transitions. And if we have already non-determinism, then the epsilon transitions is not a big deal at all, or vice versa. So it's just a little extension. And in fact, we do know that these types of machines are equipotent, so we don't increase the set of languages that are accepted. So these are just regular languages. So it is true that for any finite state automaton, we could construct a non-deterministic finite state automaton with epsilon transitions that can be reversed without any problem. And of course, those are also, as I just said, are equivalent to finite state automaton. Now here is yet another idea, maybe, and I think that it's sort of very computer sciencey. We could think about reading a symbol reversed by writing a symbol. And reversing the reading of a book is writing it. Again, notice that I was trying to be funny here. So the finite state automata, of course, they only read. So we would need to go to the non-deterministic finite state transducers. And these are, again, well understood, well researched, but not full-fledged models of computation. And we do know that they produce regular languages. Here is a little bit of notation that pertains to the fact that if there is a comma between, let's say, two letters, then that's just an abbreviation for two commands, and similarly sigma ABC. And this pertains to the next slide, where I have a transducer and its reversal. And I claim that these are the languages that are accepted and produced, and I'm sure that you will see that this is the case. So here is a finite state transducer non-deterministic, the top one. So this is the transducer, and the labels are read like if the letter read is A, then the transducer is printing 1, and from Q1 it goes to Q3, etc. And it's reversed, as you can see. This is now the initial state. This was the final state before I changed this to the final state, and the arrows are reversed. I didn't reverse the order, so it's still assumed that, let's say, one is read, then one of A or B or C is written. So this is just an example, so it can be done. Now I want to focus on abacus machines, or abaci. So why abaci? Well, it's a cool, as I say here, cool Latinized plural of a word that is of Greek origin and ultimately comes from Hebrew. But more importantly, or more seriously, these machines were introduced by Melzack in 1961, and they were immediately simplified by Lembeck in the same year. And one of the reasons why they were introduced is because they are concerned with counting rather than reading symbols or writing symbols like Turing machines or finite state automata. And in fact, I'm interested in them because they are close to counter machines or ACMs or Minsky machines. They are simple and deterministic, and they are provably equivalent to recursive functions. In fact, Lembeck in 1961 proved this, and it's also proved in Boulos and Jeffrey. So in sum, they are elegant, well-known, and powerful. I'm not that completely sure about the well-known, but they are elegant and powerful. So here is a sort of an informal description. There are infinitely many registers, and of course, finitely many of those is used in any concrete abacus machine. And each register can contain an arbitrarily large non-negative integer. And there are essentially two operations. One of them is adding 1 to the content of a register, or subtracting 1 if it is possible to subtract 1. And notice that in this description, I did not give the sort of the go-to parts of these instructions. And the reason for that is that the next page contains an example again. So the top version of this machine that I called by this. Maybe I shouldn't try to go to the edge because I'm. So this is the machine that when I constructed it, I thought that what it does is computes the absolute value of the difference of the numbers in register 1 and 2. And this is in the notation of Boulos and Jeffrey. So here the instructions are in the nodes. So for example, here, this instruction means that register 2 should be decreased by 1 if possible. And then the computation goes into this direction. And if it's empty, then it goes into this other direction. And if something is added, so for example, register 1 is increased by, or the content of it's increased by 1, then there is just one arrow coming out into proceeding. And the convention of Boulos and Jeffrey is that if an arrow ends in the sort of the emptiness, then that's where the machine stops. So it's there is nothing here because they, by convention, assume that the machine halts there. Now, the original notation of Lembeck is more like this, where there are nodes and the nodes are labeled and the instructions are on the arrows, so to speak. And so these two machines are equivalent. The difference, as you can see, is that there is an initial node here. So N0 is where the computation starts. And I added here this N labeled by the serial number infinities to make sure that it's sufficiently large so that we don't need to increase this in when we talk about in general about this final state. So, so the reversal of an abacus machine is again motivated by this idea of reversing the action on one hand, and also the direction between the moves between states. So I want to reverse the arrows and exchange the initial and final state that have these labels n0 and then infinity. And so the R plus goes to R minus, and the R minus goes to R plus, and the empty transitions, so the transitions on the empty register are unchanged. So the previous, so the transducers and the FSAs sort of contribute this idea of reversing the arrows. That's what we really want. So from the triples, starting from there, and the reversal of the reading as writing here, that is sort of captured by this idea that +1 is reversed by -1. So if we add 1, then in the other direction, or the reversal of that is subtracting 1. So what I want to observe here is that this is a non-deterministic notion that results for similar reasons as before in the case of the transducers and finite state automata. It is also something that I want to point out, that now it is no longer true that the reversed abacus machine has the two types of instructions that was originally the only types of instructions in an abacus machine. And so these machines, the Sukaba machines, may get stuck, so to speak, without looping. And this is not possible for an abacus machine. So of course, it's not decidable whether an abacus machine is going to hard, but we do know that it's not going to get stuck in the middle, so to speak, like, for example, in the case of, I don't know, Turing machines, depending on how the initial and final configurations are defined, it's of course possible that a machine just gets, I don't know, stops in the middle in some non-standard configuration. And that's not possible with an abacus machine, but it's possible with these reversed abacus machines. And I don't want to allow, of course.
Sorry, 1 second. You have about 5 minutes left in order to leave 10 minutes for discussion, just so you know. Sorry about that.
Yeah, I think that I will be finished in 5 minutes. So I want to point out, thanks for that. So I want to point out that the rearrangement of the arrows is not allowed. So what I'm thinking about is just taking an abacus machine and reversing the arrows and changing the labels accordingly. And notice that a permutation of Sukaba gives us an abacus. So here is an example where I didn't relabel in this case the initial and the final state, but this is the reversal of the previous abacus machine. And I have here the question, what does this machine do? And I have actually written down, so I try to figure out what it does. But notice that if you take a look at this arrow and this arrow, then it's very obvious that the machine is not going to do anything if the second register is not, if the second register is not empty, because it cannot transition through those two arrows. So I do claim, and so this is the claim that I made in the abstract as well, that the reversal of an abacus machine gives us a weaker machine than what an abacus machine itself is. And this is different from what happened in the case of finite state automata and finite state transducers. And so the claim is that they cannot compute even primitive recursive functions. And here is the idea of, let's take the initial function, which is the one place 0 function. So for any x, it gives us the value 0. And so it should be the case, if we can compute this, that there is at least one node with a reflexive arrow that is labeled by R-1. We can again use the pigeonhole principle. So we do need to have something like this. So for a minute, forget the other arrows, and just what I circled is what we do need to have. Now for that, we do need to have a configuration in abacus, which is on the left-hand side, a node with a arrow labeled with R+. But notice that, although we know that if this is a state that is accessible in an abacus machine, that there is going to be at least one incoming arrow. But the point is that because it is a plus arrow, there is no other outcoming arrow from this node. It cannot be the case because then it's not an abacus machine. And so we end up having this configuration where there is no incoming arrow into this node N because we reverse the arrows. So the positive loop, so this positive loop here, led to an inaccessible state because there is no incoming arrow to this node in the reversed abacus machine. So the conclusions, I want to just again to restate the comparison with what happened in the case of finite state automata and finite state transducers. So in both cases, I argued that we do need to have non-deterministic notion for the reversal, and that might not be a problem. But I do claim that the reversal of an abacus machine is, in fact, gives us a weaker machine than what we had in the abacus machine itself. And so now, turning back to the case of the linear logic case, definitely there is no proof of the undecidability of the halting problem for the reversed and branching counter machines started with all registers empty. So just that there is no such proof in the literature because nobody really thought about these machines, because I'm not sure whether independently of the proofs in linear logic, whether anybody would think about these machines at all. And so the logical aspects, I would like to reiterate that I think that the Kripke method is an excellent tool for logic or a beautiful piece of mathematics. And depending on your attitude toward logic, you might want to think that it is useful or desirable to prove a logic decidable. If you think that you want to prove it, then this is certainly one of the methods to try to do that. And I do claim that we have proved the linear logic decidable in 2015. And remarkably, there is no counterexample to our proof since 2015, so in the past 6 or so years. Thank you for your attention, and here are some references.